Hello and welcome. In this video, I'll be covering section 7.2, which is over some of the identities, specifically the cofunction, double angle, and half angle with these trigonometric functions. So my goal for you by the end of the video is to be able to utilize any and all of those identities as I just mentioned, to be able to either derive some identities or to be able to find some specific function values of either twice an angle or half of an angle if I actually know one of the function values for the specific original angle. The last thing will be being able to simplify trigonometric expressions that contain some double angle or half angle identities, which is again relatively similar to what we had covered in the previous section 7.1. So similar to last section, it's just going to add on a few more identities either to have written down in our notes. So each time these pop up on the screen, either copy them down for your own reference, or they also should be inside of the notebook where you can reference relatively easy there, or potentially even on one of the formula sheets that you've potentially gotten inside of class. So all of these for this section will be more utilizing the cofunction identities, the double angle identities that you can see here, and then there's also some half angle and power reducing ones that will be on the next slide. But again, each one of these has its own use. The cofunction identities basically are taking advantage of the ability to maybe reference from one angle to another angle on a right triangle. So notice pi halves would be the same as 90 degrees. So really it's like whatever the complementary angle is with whatever theta is, it would essentially then turn into whatever its cofunction is. So sine turning into cosine and so on and so forth. Again, these ones honestly are relatively rare. It's just on occasion we may actually be asked to prove that that identity is true, and in fact one of the examples will do that. Now as far as the double angle identities, if we wanted to actually derive those somehow, some way, since we have addressed the sum and difference formulas, specifically the sum formulas is what would happen here, because if you think in terms of what is really 2 theta, well 2 theta really would be like doing sine of theta plus another theta. So if I utilize the sum formula from before, it would just become the sine of the a value, which in this case, if I identify it, this would be like my a and my b for this one. It just happens to be they both are theta each time. So it'd be sine of theta times cosine of theta added with sine of the b value theta times cosine of the a value theta. So notice again, because the angles technically are identical, or it's the same angle both times, even though the formula had it as like 2 separate ones, if they had the same value, I end up getting, as you can see here, sine of theta cosine of theta added with another sine of theta cosine of theta for a total of 2 sine of theta cosine of theta. Hence the formula that's written above right here. So instead of me going through and deriving all of those, again, it would just be utilizing all of the sum formulas from the previous lesson to come up with them. Now the cosine, as you can see here, the cosine double angle formula actually has, if I get rid of all of this other stuff that's distracting, the cosine actually has 3 different versions, and it doesn't really matter which one you use. All 3 of them give you the same result. So it's really just a choice of, do I do the first one, the second one, or the third one here? And you really can kind of just base that on what function maybe do I know. If I only know sine, then I would say maybe use the middle one, because it's the only one that requires you to know sine. The bottom one, if you knew cosine, that would be the easiest one to use. And if you actually knew both sine and cosine, may as well just use the top one. After all, they would both have the hypotenuse being squared in the denominator, so they would already have a common denominator. Whereas the other ones that have like this +1 or a +1 or a -1 with it, I'd actually have to get a common denominator to be able to combine those things together. So again, we could derive those. The reason that those 3 have those, I guess, options is ultimately I could replace the sine squared here with its equivalent value 1 minus cosine squared, and then the minus that's in front of it would distribute through, so I'd have 2 positive cosine squareds, hence the bottom one. Or the other option would be to replace the cosine squared of theta here with its equivalent identity 1 minus sine squared, which then would turn into 1 minus sine squared minus another sine squared, which matches the middle one. So not that you really have to go through and derive each one of those, but the reason why those exist is ultimately I have the ability to, with the Pythagorean identities, replace either sine squared or cosine squared with its actual Pythagorean identity, and then combine some like terms as needed. And then again, if I wanted to derive the tangent double angle formula, it would just be utilizing the tangent sum formula with a pair of thetas On top it would be tangent of theta plus tangent of theta, hence the 2 tangent of theta on top. And on the bottom I would have 2 tangents being multiplied, hence the tangent squared on the bottom. So again, if you really wanted to see how those happened, by all means you can come and ask and I can walk you through it. But we can also just take these at face value. Those are the formulas we're going to use anytime the angle inside is being doubled. Some other ones that we have that are related to the power reducing identity actually is, as you can see, there's a cosine double angle formula here that gets utilized, but if I needed to actually replace sine squared with something that maybe didn't have a power, in other words, if I didn't want to use the Pythagorean identity version of it, I technically can do what's called power reducing, so it turns a power of 2 into an expression that now has a power of 1. It just actually is a version of the double angle formulas that we had mentioned earlier. So the top one there would be the double angle formula for cosine of 2 theta, where we just isolate the sine squared. I believe it was the middle one on the previous slide, but again, it's just different versions of that cosine double angle formula, just picking each one and isolating something different by moving things around. So the top 2 end up creating that. And then the bottom one, really, if you think about it, tangent squared is the same as doing sine squared divided by cosine squared. So if I took these 2 results and divided them, I would have to flip the second one. So notice the sine, which has the minus, that's why the minus is on top. And then the cosine that has the plus, when I flip it, would now be on the bottom. So that's why that has the addition on the bottom. So the bottom one really is just a combination of the top 2 when it really is all said and done. As far as the half angle identities, these ones are ones that are a little bit tougher to derive, but again, it really just kind of comes down to just recognizing when I need to do that and then referencing the correct place on our pages or in our notes. So for each of these, notice there's actually a plus or minus symbol I may have to worry about, and that is 100% reliant on wherever that angle is. So whatever the angle is inside, whatever quadrant it lies in, just be aware of like whether the sine or the cosine or the tangent should be a positive value or a negative value. Honestly, with the tangent one, you can actually get rid of that plus or minus right here by just utilizing one of the other 2 versions, which are essentially by multiplying the top and bottom of what's inside of this radical by the conjugate of either the top or the bottom. Just kind of depends on which one you went after, and then simplifying, utilizing some of the trig identities from last lesson, and then seeing what it would turn into. So it actually would end up squaring the top, so one of them, or squaring the bottom, depending on what you were multiplying by. So the square and the square root would cancel out, hence where the radical is kind of disappearing. And then the other part, if you actually went through and did it, would either turn into a sine squared on top or a sine squared on the bottom if we utilized a Pythagorean identity. And then that square and square root, again, would cancel, hence why it's just a single sign. If you, again, really wanted to see how the other 2 or the bottom 2 got derived, go for it. I honestly would say let's not even worry about that one and just choose either the top one here or the bottom one there. Those usually are the better versions to use for a half angle formula for a tangent. Alright, so now that we have all the identities that this video will be discussing or utilizing, let's go ahead and jump into some examples. So pretty much everything from here is just more examples, so just try and follow along, engage with it, kind of think about the why or how any of the steps happen. Here it's actually wanting us to do one of our first proofs of an identity. So this is, as far as an approach is concerned, it's usually best to try and pick whichever side is the more, I guess, quote-unquote ugly side or more difficult in appearance. So I think hopefully your eyes got drawn more to the left side than it is the right side, because that would be the more difficult side. And if we look at what really is happening there, it's just a sine of 2 angles that are being subtracted. So really this is from last class utilizing this sine of A minus B formula or identity. In this case that would be sine of A times cosine of B minus sine of B cosine of A. Should have given myself a little bit more room, but again, that would just be one of the formulas on our reference page, and ultimately all this is wanting us to do is just prove that that identity is true. So I'm basically going to try and pick the left side and manipulate it until it matches the right side. So if I go through and do it, I just kind of know my end goal is to make it turn into cosine of x somehow, some way. Ultimately this formula is actually going to kind of do all that work for me. So if I just go ahead and follow that formula, this thing that I've started with here, I can kind of identify that the A values are going to be pi halves, and the b values are just going to stay x's. So now at this point it would be sine of the a, so sine of pi halves, times the cosine of b, well that's just going to be cosine of x, then minus, since it's a subtraction here, it keeps the subtraction, and then now it's going to be sine of the x, or the b value, times cosine of the a value, which was pi halves. At this point we should recognize that pi halves is one of the angles on the unit circle that we can reference. Sine of pi halves has a value of 1, so this will turn into 1 times cosine of x, minus, I'd have sine of x still here, times, and then cosine of pi halves actually is 0. So since that whole thing there is being multiplied by 0, the sine of x term kind of just goes away, or it gets canceled, and 1 times cosine in this case turns into cosine of x. And as you can see, this that we just had matches that. So technically the proof part is actually all of the work that I did from start to finish until it turned into what it was supposed to turn into, which happened to, for this specific problem, be cosine of x. Now with our next example here, now notice it's providing us with some information to start. Specifically, it's giving us a tangent ratio. So kind of similar to what we did with the sum and difference formula, I would recommend right off the bat, if they ever give you a trig ratio of any sort, go ahead and draw a triangle for that specific angle. In this case, the angle is just being named theta. And at this point I should be able to label a pair of sides where I've got a 3 and a 4, but it does say it's in quadrant 2. So if we think about quadrant 2, how that would work here is going to be the horizontal edge should go negative, whereas the vertical would go positive. So that tells me that for sure I've got a negative down here on the bottom edge, but a positive on the vertical. So if I know that the opposite must have been a 3 and the adjacent must have been a 4, that kind of helps us determine that in this scenario, which should be the x value or the horizontal that would get the negative, so that technically makes the 4 have the negative. And now if I do Pythagorean theorem, I should be able to square both of those, add them together, so 9 plus 16 would be 25. Square root of that would give me 5, so I may as well just go straight to saying that's 5 as the hypotenuse. Or you may have just recognized that that is a 3, 4, 5 triangle that is kind of nice to deal with. It pops up quite often. So if we already know those ratios of sides, we can take advantage of that info. Now from here, it just wants us to figure out what the sine, cosine, and tangent of twice the angle would be. So even though I don't know what the angle is, let's say hypothetically I know it's in the second quadrant, so I know it's got to be more than 90 degrees but less than 180 degrees. This is basically a formula that if I doubled it, so let's say it was like 120 degrees, if I double that it would now be 240 degrees. Obviously that would not be an example that it would want us to do because, well, we already know those angles on the unit circle and what the ratios are, but I hope that makes sense. Maybe I could have done something like maybe it's 100 degrees, so its doubled angle would be 200 degrees. So it would be like we're trying to compute what that double is, even though I don't know what the specific original angle was. Regardless, I'm just going to identify what formula I need. So for this one, sine of 2 theta requires that double angle formula, which from earlier or on a reference page if you have it nearby would be 2 sine of theta cosine of theta as the formula I need to follow. So notice all I would need to know is whatever the sine of the angle is and whatever the cosine of the angle is. I'm going to multiply them together but also double that result. So if I go ahead and replace those things just like we did before, sine of theta from our triangle we can hopefully see to be 3/5. Cosine of theta from our triangle we can see as negative 4/5 using the adjacent and hypotenuse. And if I multiply those two things, or actually these three things together, if I did 2 times 3, that would give me 6, times a negative 4 would give me a negative 24. And then on the bottom you can kind of picture like the 2 is really over a 1. I've got a 1 times a 5 times a 5, which would turn into 25. So the sine of the angle that would be twice as big as whatever this original theta is something that would come back as a ratio of negative 24/25. For cosine of 2 theta, we've got 3 different options we can go with. I'm going to go ahead and just go with the first option that was in the list and just utilize cosine squared of theta minus sine squared of theta. But again, there were 2 other options I could go with if I wanted to use them. It doesn't really matter. They all 3 give you the same result if you do all of your simplifying correctly. So for this one, I'm going to go ahead and just replace each of those parts with their values. So this would be cosine of theta that I start with, negative 4/5. But that quantity is being squared since it's a cosine squared. then minus the sine ratio, which was 3/5. That also is being squared, so I will need to do a little simplifying here before I can combine them. If I square each of these, the negative actually will go away on this first one and become a positive 16/25. The second one would become a 9/25. Notice the subtraction still is between. The subtraction was not attached to the 3. The 3 was actually separate, or the 3/5, if you want to think of it that way, was separate. The power was only on the positive. The subtraction stayed in the middle. So now if I actually do subtract those, they already have a common denominator, which is convenient. 16 take away 9 is 7, and then the common denominator of 25 just tags along. And there we go. We have now our cosine ratio for whatever that double angle happened to be. Now at this point, since we have found the sine and cosine, we could utilize a quotient identity, and to determine tangent of 2 theta would just be those two things divided. So it would be keep the first fraction, divide by the second, so flip the second and then multiply, so the 25s would cancel. We can kind of see already this would become negative 24 over a 7 if we were to flip the cosine and multiply. Again, the 7 would now be on the bottom. But just in practice of utilizing the formula that we actually have, let's go ahead and see how that would work if I hadn't done the work to do the sine and cosine. We can just use the tangent formula. So for this one, it would be tangent of the theta, but doubled all over 1 minus the tangent squared of that theta. So this is where I can now substitute whatever the value is in from our triangle, or actually this one was the one they gave us, so it's going to be twice the negative 3/4 over 1 minus the negative 3/4 being squared. So notice I did have to group the negative that was on that 3/4 inside the parenthesis this time, so the squaring part actually is going to make that ratio become positive, so the subtraction that is there stays there. So this would be 1 take away. If I go ahead and square the bottom, that would become a 9 over a 16. The top, if I go ahead and multiply it, that would become, actually I can say the 2 and the 4 can reduce to a 2 and a 1, so that's really just a negative 3 over 2. And now if I wanted to clear out the fraction that's inside of the big fraction, notice there's actually 2 of them, I would just do whatever the common denominator would be, which in this case would be just multiplying by 16, and if I distribute that through, the top multiplying by 16, I don't know what happened to the 1 there. I thought I wrote it, but times 16, there we go. For this one, it would be now 16 divided by 2 is 8, then times negative 3 is negative 24. On the bottom, if I distribute the 16 through, it would become a 16 take away a 9, which then turns into a negative 24 over, in this case, it would be over the 7. So as we already could kind of see from taking the previous two answers and dividing them, the double angle formula for tangent still does technically do it without us needing to have to use the quotient identity. Having already done the sine and cosine, since we already did the legwork, it actually would probably be better to just divide those two if I had this as like a 3-part problem. But if the problem only wanted us to do the tangent, it really doesn't make sense to do all of the work for the other two and then have to do something extra with those results. Why not just utilize the formula we have, and it takes us straight to the answer just like this one did. Now as far as what quadrant would this lie in, we could now look at our 3 results and go, well, sine is negative, cosine is positive, and then this tangent value was negative. Where do those 3 things happen? Well, if cosine is positive, it has to be on the right side of the unit circle. If sine is negative, it's got to be on the bottom, so that would mean this has to be a quadrant 4 angle. Now whether it's 1 or 2 or 3 or 4 rotations around the unit circle, we don't necessarily have enough info to know right this second, but as far as the end result, based on the ratios and what type of numbers we got, we can now confirm for ourselves that that actually would be an angle that lies in the second quadrant, even though the original angle that they gave us was in the would be in the fourth quadrant, even though the original angle they gave us was in the second quadrant. All right, let's go ahead and try another couple here. I think we got 3 more examples. This one's got kind of 2 parts to it, but for this one, it just wants us to basically find a way to rewrite utilizing some of those identities that we have and try and turn it into potentially an easier thing to deal with. Or this first example really is just trying to get us to change from either being triple an angle down to a single angle, which then might be easier to actually compute out. But anyway, as far as the approach for this one, it would be more of a, let's just take what we have. If it says 3 theta, one way that we could rewrite that is saying 2 theta plus another theta is equivalent to 3 theta. And now utilizing maybe a sine sum formula, since it is technically sine of now 2 things being added together. So this is now kind of telling us that our a in the formula is going to be 2 theta, our b in the formula is going to be 1 theta, and now just plugging in. So this would be sine of 2 theta times cosine of 1 theta added with sine of 1 theta times cosine of 2 theta. Again, that's just using the sine sum formula from our identity sheet or our reference page. From here now it would be, let's look at, we've created a couple of double angles. We have a couple of 2 thetas. Again, our goal is to try and turn it into just 1 thetas. So we do have some formulas that would allow us to do that. In this scenario, I've got 2 sine of theta cosine of theta that can get in place of the sine of 2 theta. That's just its double angle formula. So that was all just this guy right here. I still have the times cosine of theta that was extra from that first term. Then I add that with the sine of theta that's already there. That's already a single theta, so that's good. But then it needs to multiply with whatever cosine of 2 theta is. So if we go ahead and maybe try and replace that with something that we know, I feel like maybe just going with the first version, since it does have 3 versions. I could choose any of those 3, but I'm going to go with this one just to see what kind of happens. So if I go ahead and simplify that way, I can now maybe distribute that out, get my parentheses, but also combine some like terms with this first one. I have 2 times sine of theta times, and then if I notice I have a cosine times a cosine, that becomes a cosine squared of theta. Added with, and if I distribute this through, I've got sine of theta times cosine squared of theta for the first term, and then sine times a sine squared. If I go ahead and do that one as well, it will turn into a sine cubed of theta. And peculiar enough, here those first 2 terms, 2 sine of theta cosine squared of theta, added with another sine of theta cosine squared of theta, can actually combine and turn into 3 sine of theta cosine squared of theta, and then minus sine cubed of theta. So technically I was able to turn all of my angles into just single thetas. Right now I don't necessarily feel like I would be a big fan of having a cosine in the middle of all of this, so I might continue on and just try and attack this cosine squared term, which has some options. I could replace that with 1 minus sine or 1 minus sine squared of theta, and then just kind of see where that would go. But technically right now I've satisfied what the question required, so all of this would be just like extra and more of a personal preference thing, not so much a final answer for this. So that's kind of the open-endedness of this one, is it just wanted us to make it such that it was an expression that was somewhat simplified as best as possible, where all of the angles inside were just single thetas. I've satisfied that. All of these do have just a 1 theta inside, so I've technically answered it. But like I said, I would probably try and replace the cosine squared with 1 minus sine squared, multiply things out, and then rewrite it in terms of just one function instead of having 2 different trig functions. But again, that's more a personal preference thing, not so much a requirement of the problem. So I'll go ahead and call that for the video here good enough, but technically there are some more steps that we could do if we really wanted to, which is kind of the beauty, but also the horrible nature sometimes of trig, is you can continue on and kind of get into a little bit of a spiral and not know exactly when to stop. So for this one, I've satisfied the question, so technically I guess this is a good stopping point. Looking at the second one here, it looks like here it wants us to more just try and take something that has a power and rewrite it using something that doesn't have powers or just has powers of 1. But it is allowing us to have at least an angle of x or potentially 2x on the inside as like our approach. So again, with this one, it would be more of a, let's just look at what we're starting with and see if we can rewrite it. Cubing something would be the same as doing something squared times an extra something. So if I just start by maybe just rewriting it now as a product, cosine squared of x times cosine of x, that still is the same as cosine cubed. I just now have the ability to maybe utilize some of the formulas that we've seen prior in the video. So one of those happens to be what is the power reducing formula for the cosine squared. which honestly, if we wanted to maybe see the side work of that cosine squared of theta, if I think in terms of having the cosine of 2 theta being equivalent to 2 cosine squared of theta minus 1. It was, I think, either the middle or the last option of it. I think it was the last one, if I think back correctly, but regardless, it doesn't matter. If I now just said, let's get this by itself, all I would do is add 1 to both sides to start, and then eventually I would have to divide by 2. And notice we get this formula that would be 1 plus, if I go ahead and write this down, 1 plus cosine of 2 theta all over a 2 that then is going in place of this cosine squared of x that's right here. Then I still have the extra times cosine of x. I don't know why I wrote theta. That should have been an x. And I still have the extra cosine of x that's there. And so at this point we can go ahead and say we've satisfied everything. I don't have any powers right now, so I've checked that box of I have everything to the first power. And all of my angles are either x's or 2x's. Well, I've got one angle that's 2x, one angle that's 1x. So at this point, just within like basically 2 steps in utilizing that power reducing, or technically the power reducing is just take the double angle formula for cosine, but then isolate the cosine squared. It also would work if I wanted to choose the version that only has sine squared and isolate the sine squared. I could also use that to my advantage, but again, it's one that could be used. It doesn't happen to pop up a whole lot in this class. This is just one of those examples, but if you needed to do like a power reducing, notice it actually does work, and it turns into something that now has no powers at all, which might potentially be easier to deal with if I had to do like a secondary step after this. Moving on to our last couple of examples. So far we've only been really talking about how we can maybe utilize or prove the cofunction identities. We also had some examples where it was utilizing the double angle. The one thing we haven't really seen examples of are the half angles. This happens to be one of those. Now, as far as how would I know to use a half angle for this one, well, if this problem was presented to you, let's say last section, I assume you would look at that and go, well, let's see if there's a way I can rewrite maybe that using a pair of 8s, and then maybe add them together and see if I can actually get that to work out. So if we thought of how could I get 1/8 if I'm adding or subtracting here, well, as long as I have 2 consecutive numbers, I would be able to do that. So for example, I could do like maybe, I don't know, let's do maybe like 5 minus 4. Regardless, because they would have to be side by side, and in fact not addition but subtraction, the issue that we would run into is, notice only one of the fractions each time would reduce, because, well, if they're only separated by 1, then one of them is going to have to be an odd number, and that won't reduce with the 8 that's on the bottom. So no matter how many times you try just picking a pair of numbers and subtracting them to match the value that's here to start, there really wouldn't be anything that would ever pair up as 2 angles that are on the unit circle like the sum and difference examples we had last section would be. So with that being said, we now have the ability to think, well, maybe instead of me thinking about adding or subtracting to get a number, in this case pi-8ths, what if I said, what is pi-8ths half of? So it's kind of like we're going to solve this expression of pi-8ths is technically equivalent to some angle here divided by 2. Well, what would that theta need to be? Well, technically I would want to multiply by 2 to figure out what that number should be. Here, if I multiply by 2, I get 2 pi-8ths, which reduces to pi-4ths. So in this scenario, the theta that I would want to put into the formula here is going to be pi-4ths. So to kind of show what that would look like, essentially what I'm going to do is rewrite this as, instead of it being tangent of pi-8ths, I'm actually going to say it's tangent of pi-4ths cut in half. So now we can kind of see from our formula, which I believe they use an a in the formula, that technically the a value I just identified is the pi-4ths angle, because that's what's being divided by 2. So now if I go ahead and use that formula, tangent was the one that had like 2 other options. I recommend using the options that don't have the plus or minus a square root, because then you don't have to worry about dealing with that plus or minus symbol. So I'm going to choose the one that just has the 1 minus cosine on top, because I don't really like having 2 terms in the denominator. So it would be 1 minus cosine of the angle that I just got, pi-4ths, or just identified, not so much got. And then it would be over the sine of whatever that same angle is, so in this case still pi-4ths. And notice at this point now I should be able to, because those are that is an angle from the unit circle, I should be able to replace them with their values. So if I replace them with their values, it would be 1 minus, well, cosine of pi fourths is rad 2 over 2. So I'll put that in that spot. And then sine of pi fourths just also happens to be rad 2 over 2. And now if I go ahead and try and simplify, we can look at what we have and go, well, I don't like the fractions inside of the fractions, so let's maybe just distribute a 2 through on top and bottom to simplify it at least a little bit, get the ball rolling. So if I distribute the 2 through, I end up with 2 times 1 is 2, minus, and then 2 times the rad 2 over 2 would cancel the 2 2's in the denominators to leave just the rad 2. And similarly on the bottom, the multiplying by 2 just leaves a rad 2 there as well. So now my only thing I have to worry about is, well, I still have a radical in a denominator, so let's maybe just rationalize by distributing through a rad 2 on top and bottom. This one's kind of nice because it's just, again, a single term, not a double term, so I don't have to think conjugate or anything weird like that. Here it's just going to be rad 2 times rad 2 is 2, and then multiplying through on top, I'd get 2 rad 2 minus the regular 2, because it's going to be rad 2 times 2. And notice all of those do reduce. I can reduce or cross out all of the 2's because they're all divisible by themselves in this scenario. And I get rad 2 minus 1 as like my final answer. So the tangent of this pi 8's angle technically will come back as a ratio of rad 2 minus 1, whatever that might be in decimal form. And we could also check our work here by figuring out what that decimal is, and then comparing it with doing tangent of pi 8's, making sure that the mode is in radians, and comparing the two decimals. And if we happen to do that, or take the time to do that, we would recognize that we technically have the exact same, which would then prove that we did all of our work correctly. But this, again, is kind of tricky at the beginning, is you have to think of, like, what is the angle I'm starting with actually half of, and then whatever that angle is actually going to be what goes in the numerator over the 2, and then notice I just use that angle the rest of the way. That over 2 part is really just helping us identify, like, oh, I'm needing to use a half angle formula. That's about it. So again, we kind of almost work backwards to start. We double the angle to figure out what it would have been half of, and then from there just kind of let the unit circle references take over, where I replace them with either rad 2 over 2's, rad 3 over 2's, or maybe 1/2's, since those are all the ratios of sine and cosine on the unit circle. And again, if I'm in a different quadrant, maybe I'd have to worry about some negative signs as well, but in that scenario, it's not that much more difficult. Just be a little bit more mindful of what happens if I multiply 2 negatives, or add or subtract with negatives, and that sort of thing. All right, moving on to our last couple of here, which are just some practice again of how do I manipulate these things to simplify them in some way, shape, or form. So really it's just kind of a, what do you see, what can we try? We're just going to hope that we can turn things into relatively easy replacements. Here, the first thing for part A that I notice is I've got a fraction inside of a big fraction, so I kind of would think, you know what, I don't like that 1/2 in that spot. So let's just multiply the top and bottom by 2, so that 1/2 would cancel with the 2. And notice that would now give us 2 sine of x cosine of x on top now, and then the bottom would now just be cosine of 2x. Some of you might be tempted to cross out the cosines right now, but notice again the cosine on the top actually only has 1x in it. The cosine on the bottom has 2x in it. If it helps, you can also start throwing some parentheses around the angles themselves so you don't accidentally start crossing some of them out, because some of you might also be tempted to cross some of the x's out. But again, all the stuff that's inside of the trigonometry or trigonometric functions is technically kind of in an untouchable area, and it can't really interact with anything else unless I apply some identity that allows for that to happen. Now for this example, I hope we can recognize the top here actually matches one of the formulas we've talked about earlier in this video, which is that references, or actually is equivalent to, the sine of twice x, right? So the 2 sine cosine, if you recall, was sine of 2x's formula. So normally we've been starting with the sine of 2x and then splitting it up into those two, but it also works the other direction. The denominator, on the other hand, I'm just going to go ahead and keep in that format, because now I actually have 2 angles that do match. So now I can actually utilize maybe some of the other identities from earlier, which this is, if you recognize, a sine over a cosine where the angle is the same. That turns into a tangent. So this actually is the same as saying what's tangent of 2x. And voila, we've been able to simplify what was relatively ugly at the start into a semi-nice. I mean, it still has 2x on the inside, and technically I could make this worse if you really wanted to, and use the double angle formula for tangent and turn it into a fraction. But I feel like this, because the next step would make it uglier, is the best stopping point for this specific simplify problem. Now if we look at the next one, try and think in terms of what are some options that we could do. We could try and find ways to maybe manipulate this half angle idea. We could also maybe try going after the power. We could maybe try and find a way to maybe replace sine squared with maybe cosine squared. We got quite a few more options with this one when it's all said and done. We just ultimately need to pick one and go. So for this one, I'm thinking I don't really like having the power of 2 intermixing with something that doesn't have a power of 2. I could technically try and turn it into the cosine squared like I mentioned, and then maybe treat it like a quadratic, but I don't really want to have to try and do quadratic factoring either. So I'm just going to go after this sine squared and utilize its power reducing formula, which its power reducing formula was 1 minus cosine of the angle doubled, or twice the angle that was inside. So in this case it would be twice the x over 2 all over a 2, and then that all is still being added with the cosine of x that was on the outside or separate after that plus sign. So again, all I did was try and go after this part right here, just utilize the power reducing. Notice the 2 that's in front stayed here and the cosine of x stayed here. So I didn't really manipulate anything other than what I just put parentheses around, or whatever I'm circling right there. So that's all I really did, was replace that. Everything else stayed identical. Now it's a matter of what can I maybe simplify inside there. Well, I think we should all hopefully see that the 2 divided by 2 inside of the cosine will cancel out, and then this 2 that's in front divided by 2 will also cancel out. So it turns into a relatively nice expression of 1 minus cosine of x, since the two 2's have canceled, then added with the other cosine of x that was on the outside already. And I'll go ahead and throw some parentheses around that just so we can kind of see some similarities, or maybe show that the angle is truly inside of that function. Now what also is kind of nice about that is I have a negative cosine of x plus a cosine of x. Those two are actually going to zero themselves out. So all of that ugliness at the very beginning actually just turned into a value of 1. And since it's 1, technically there's other options we could turn it into. We could make it sine squared plus cosine squared, one of the Pythagorean identities, or there's 2 other versions that have equals 1 as well. But again, that would be making it worse, hence why this would be the most simple version, because the next step doesn't really improve it anymore. I don't really know how we could improve a single number or a single numerical value like that. Make that look a little bit cleaner there. That was a weird box. But the value there would just be a 1. So anyway, hopefully these examples help kind of solidify how these new formulas or identities can get involved with some of the simplifying things, as well as how we can maybe simplify some of the double angle and half angle values utilizing maybe angles from a unit circle, or we could even do from a given ratio by drawing a triangle. But yeah, hopefully again this is helped with at least giving you a starting point for any of the problems that you'll see either on quizzes, assessments, or homeworks, or whatever it might be. But anyway, as always, if you have questions, just come find me. We'll see if we can work it out, work through a few more examples one-on-one. Hopefully you can make it click. But as always, I also appreciate you watching this video if you've taken the time to do it. We'll catch you next time.